Imagine robots that can do everything, just like those in cartoons, carrying groceries, cooking meals, and even taking care of pets. Sounds like a dream, right? However, training robots to perform various tasks in unpredictable real-world situations is quite challenging. Traditionally, this required collecting vast amounts of specific data for each individual task, which can be incredibly time-consuming, costly, and restrictive. But researchers at MIT, with support from tech leaders like Meta, might have found a solution. They've developed a smart method for training robots inspired by large language models. Similar to the technology behind tools like GPT-4, their approach involves aggregating diverse data from multiple tasks and areas, such as simulations, real robot actions, and human demonstration videos, to create a universal robotic brain capable of handling various tasks without needing to be retrained each time. Let's explore this further. The system is called Heterogeneous Pre-trained Transformers, or HPT for short. What makes it particularly exciting is how it integrates different types of robotic data, camera feeds, sensor inputs, and human-guided demonstrations into one cohesive system. Typically, each robot has its own unique setup with different arms, sensors, or camera placements. HPT standardizes this into what they refer to as a shared language, allowing a single model to interpret all this varied input effectively. So, how does it function? The HPT system utilizes a transformer architecture, a type of machine learning model similar to those powering GPT-4, to process and learn from diverse data sources. Instead of using sentences like in language models, it works with tokens representing robotic data. Each input, whether from a camera or a motion sensor, is converted into tokens suitable for the transformer. By combining these varied data sources, this robotic brain can identify patterns and learn tasks in a more adaptable way. The results have been impressive. In tests, HPT improved robot performance by over 20% in both simulated and real-world environments, and it even managed tasks it hadn't been specifically trained for. This represents a significant advancement from traditional methods that rely on narrowly focused, task-specific data. One of the main challenges faced with HPT was assembling a sufficiently large dataset for training the transformer, over 200,000 robot trajectories from 52 different datasets, including human demonstration videos and simulations. This is notable because typical training datasets in robotics often concentrate on single tasks or specific robot designs. By integrating everything into a broader learning model, the researchers addressed the issue of data diversity, which stems from various robot designs, environments, and tasks. The approach is inspired by how we train language models like GPT-4. In language models, we first pre-train the model on extensive amounts of diverse language data for a broad understanding before fine-tuning it on specific tasks. HPT follows a similar path, giving robots a foundational knowledge across different data types before focusing on particular tasks. This comprehensive pre-training enables robots to adapt much more quickly when presented with new tasks, thanks to their exposure to a wide range of data. Ultimately, the future of robotics depends on creating robots that can perform multiple tasks, just like humans. Picture a robotic arm that can assist in cooking, effortlessly transition to folding laundry, and even feed a dog, all without needing a complete retraining for each new job. The HPT model could be a significant step toward realizing this vision. Researchers even hope to develop a universal robotic brain that can be downloaded and plugged into various robots, enabling them to perform numerous tasks right out of the box. On the technical side, HPT comprises three main components: stems, a trunk, and heads. The stem acts as a translator, processing unique input data from different robots, such as visual data from cameras and proprioceptive data from sensors, into a shared language comprehensible to the transformer. The trunk processes this unified data, while the head converts it into specific actions for each robot. Each robot only requires its unique stem and head configuration, while the trunk remains universal, trained on a vast and varied dataset. This architecture allows HPT to manage data from multiple robots simultaneously, effectively treating them all as part of one extensive training network. Testing showed that HPT learned faster and performed tasks with greater accuracy compared to traditional methods. As the model was scaled up, its performance continued to improve with increased data complexity, mirroring trends observed in large language models. Importantly, HPT has been tested in both simulated and real-world scenarios. In simulations, it tackled various tasks like moving objects and interacting with different environments, consistently outperforming other methods. In real-world applications, such as feeding pets and assembly tasks, HPT demonstrated greater adaptability and robustness than traditional models, handling variations in environment and conditions more effectively. The team ran tests across popular simulation platforms like MetaWorld and RoboMimic, combining robotic data with human activity videos, such as everyday kitchen tasks. This integration allowed HPT to learn from data that included human actions, enhancing its versatility. To make this work, researchers experimented with managing the massive mixed dataset, scaling the model, and testing different batch sizes to gauge how much improvement could be gained from additional data. They found that the model scaled effectively. The more data it received, the better its performance. Future goals include investigating how even more diverse data types could enhance HPT's capabilities and enabling it to process unlabeled data, similar to how GPT-4 understands context from various text inputs. The ultimate aim is a plug-and-play robotic brain that requires no training. Simply download it, install it in your robot, and it's ready to go. When transferred to new robots and tasks, HPT showed it could adapt much more rapidly than models trained from scratch. For example, in a task involving cleaning up objects, HPT achieved a 76.7% success rate, surpassing other models. It also excelled in tasks like filling water and scooping food, consistently outperforming models that were trained from the ground up. However, the team acknowledges there's still work to do. Currently, they are focused on short-horizon tasks, those completed in just a few seconds. Expanding this capability to longer, more complex tasks is one of their next significant goals. They also aim to enhance the model's reliability, as success rates typically hover below 90%. In summary, the new HPT model marks a significant advancement in developing flexible, multitasking robots. By merging data from various sources, including robots, simulations, and human videos, they are creating a system that can more effectively adapt to new tasks and environments. While it's still early in the process, this could pave the way for robots that are significantly more capable, adaptable, and arguably human-like in managing diverse tasks. Who knows? Perhaps one day we'll all have our own Rosie the robot to assist us with everything we need. What do you think about all this? Share your thoughts in the comments. And if you enjoyed this overview, don't forget to like and subscribe for more updates on AI and tech. Thanks for watching, and